Then we talk about the how does it work between network to network. So how do you connect network to network? Meaning, how do I connect it from SUNY Korea network to the Yonsei University? How does it connect it? So we have an IT team in the IGC and the SUNY Korea. Then the Yonsei University right there has their own IT team. How they are connected and how does it work? Okay, we're going to talk about interconnecting, so internetworking today. So internetworking is arbitrary collection of networks. Like Yonsei University, their own protocol, their own policy. SUNY Korea, our own policy, and IGC has their own policy. So network 1 and network 2, how they should be connected, how they work. So between them, and we set the leaders called the routers, router 1 and router 2. This router information is maintained hierarchical. So we're going to talk about why hierarchical is more important than the flat architecture. Then, so let's say this is our SUNY Korea, and this is Yonsei. So let's say my computer is H8, host number 8. How do I connect to the H1, which is Yonsei University's one of the computer, one of the PC, from my PC? How does it connect it? Let's say this holds the CSE310 solution. Somehow they have it. So how do I connect it? So first, from me, I go to my switch, then switch go to the router of the SUNY Korea. That router goes to router of the IGC. That goes to the backbone of the KT. Then goes to the Yonsei University's the router. Then goes to this computer. Okay, then I can fetch this information, copy this information, then copy it to backward. Then I can see. Okay, that's basic host-to-host packet delivery. So how does the internet work? So common protocol that bridges heterogeneous between hosts of different types of network. Heterogeneous. The antonym for heterogeneous is homogeneous. Homogeneous meaning everything is similar. Everything is identical. But heterogeneous, everything is different. We have different policy. We have different devices. Maybe we can use Huawei, and the SUNY Korea may use a Huawei, and IGC uses Cisco. Then Yonsei University may use the Foundry. Different devices, but they all have a protocol. They have to follow that protocol. So how they connect it? So as long as they follow the common protocol, we call the IP, then it is connectable. Then even it is completely different policies, completely different devices, we're still able to connect it. So let's say from host 1 to host 8, they go to TCP, IP, and Ethernet connected by router 1. Let's say this is SUNY. Let's say it is IGC. This is KT, Yonsei. So we are connected by Ethernet, then go to the IGC router and connect it to the KTs. Then KT's router goes there and go to the IP of the Yonsei's router, then goes that computer. So if you look at it here, so these routers doesn't check about TCP. Why? TCP is end-to-end protocol. In the middle, they don't have a privilege to open it, and they don't care. So they only care about up to IP. So above there is end-to-end, okay? Meaning if your end-to-end TCP is well encrypted, in the middle, they are just delivering. They don't have ability to open. Even they just open it, that are just random numbers because your packet is encrypted. So whenever you send the messages, we do encryption. Okay. So best effort network. So IP network is best effort networking, meaning they don't guarantee. I do what I can do. I do best what I can do. Okay. So IP is the datagram connectionless protocol. It does not provide any type of guarantee about the packet delivery. So out of the packet delivery, duplicate packet, no error correction, there's nothing. So IP packets. If IP packets are lost, IP does not try to recover or retransmit. But an upper layer on TCP or a lower layer in the MAC, they may try to. For example, long time ago, maybe 200 years ago, there is a IP over avian carriers, meaning I'm using pigeons. Okay, so it also has a standard. How do you use the pigeon as a communication standard? A long time ago, we don't have the internet, so we had to use it. Okay, so that's the standard. Also have name RFC 1149. So IPOAC, the IP over the avian carrier, has implemented successfully, carrying 9 packets with 55% of packet loss and delivery delay about 1 hour, about 90 seconds and 90 minutes. So 100 minute is 1 hour 40, 1 hour 40 minute, 1 hour 40 minute, and 50 minutes. It has delay like this. We understand that, right? So if you look at the IP4 version 4 packet, so we will talk about the IPv4 and IPv6. So let's look at the IPv4 first, the basic level. Okay, so IPv4, so in the IP layer, and this is two most important, source IP and destination IP, and my payload. Okay, meaning that I have to clarify who I am, and I want to go to there. Okay, my destination and my source information. In the middle, they have all information, TTL, time to live, and time to live means if I put into the cycle, so how do I kill myself? Okay, an 8-bit protocol, and this specifies what protocol I'm using, something like UDP or TCP. So total length, how long is my packet? Therefore, I can declare, okay, until here is my messages. Okay. So let's look at one by one. Version information, what version is this? IPv4 or IPv6? So we are using IPv4 a long time ago, and we're still using it. And there is IPv6. Why? IPv4 is so limited. So we're going to deeply talk about this on this today's lectures. And header length. Header length is so number of the 32-bit word in the header, typically 5 for 25 byte for IPv4 header. So it can be more when IP options are used. So header length. How long is my header? And type of service. What service I'm doing? So if I am urgent, and if I have a higher priority, I can set my type of service higher priority. And if I don't care about the speed, but I want to have delivery, the confirmation, then I can use for the file transfer. But I don't care about my guarantee, but I want to carry it about fast as possible, meaning my voice kind of information. Then total length, to specify the length of my packet. Then the maximum size is 2/16. -1, and fragmentation information. Is this packet is fragmented or no? So we're going to talk about this. Fragmented meaning if the higher upper layer gives me a bigger chunk, IP layer have to divide their own chunk. Okay, so if fragmented is 1, meaning my packet is following, then you have to continuously take my following, then upper layer may handle this properly. Time to live is identify packets are stuck in the forwarding loop. So how can you loop out? Oh, meaning, or how can you discard this packet itself? And look at the TTL first. TTL is provide a potential robustness problem. So forwarding loop, let's say my packet is forwarded multiple times and get into the loop somehow. How can I kill it? Meaning TTL, time to live, will decremented by each router. So every router it goes to, it decrement 1. Once it reaches 0, it discards itself. Okay, so if the time exceeded, I have to discard it. In the network, it is usually set to the 7 to 20. If it is longer than 7 or 20, that threshold, then it kills itself. Meaning I can eliminate the ghost packet. Protocol is it TCP or is it UDP, or we have more protocols, something like a QUIC, something like MPTCP. We have many types of those. So we have number, standard number. If I'm using this, so my correspondent has to know, right, what they are expecting. Then they are plugging right the demux, right decoder, then they can properly handle it on their side. Okay. So checksum. Checksum is a simpler version of the CRC. So some of the all 16 bits word is a periodically the packet header. And if the packet header is properly matched, then it's not problem. But sometimes it's wrong. It's mismatched. What do? Discard it and send it again. So I just discard it in the IP level. They don't request the retransmission, but a lower layer, upper layer, they handle those. So IP addresses field. So my source and destination. My source meaning identifying the sending host, and recipient can decide whether to accept our packet. Why is this important? If the someone is attacker, then I can block their source IP. So there is a Linux called Linux Kali. That's the design for the attacking. So if you, so I did sometimes, so testing my servers, then I implemented on the AWS, my server, then I try to DDoS my server. Then multiple times of the, with a couple of times of attacking with the DDoS, then the Amazon AWS automatically blocks my source IP, meaning your IP cannot access to the that server. Okay. So if the source IP is known, then I can block my maleficent function generator. So something like this. And destination, and I have to know who's my destination. If it is not for me, I can just forward it or discard it. Two things I can do. Okay, so fragmentation and reassembly. So fragmentation, why is the fragmentation important? Let's say your backbone is different. So Ethernet or fiber optics and point-to-point just connection. Then Ethernet. Then host 1 and host 8. Host 1 was the SUNY K, and host 8 was the Yonsei University. So we have very nice backbone. Then my packet size 1400. That is fine. Then between this IGC, there's KT, there's Yonsei. So in IGC, they can handle it to the KT. The backbone is wide enough. But Yonsei University set up a long time ago, and they didn't update their routers. So I have to connect to the Yonsei, but Yonsei only support 512. Then what I have to do, I have to fragment it, fragment, then deliver to the router, that the router can deliver to host with the fragmented size, then they can reassemble on their receiving, right? So SUNY K, even they can deliver the higher packets. So all the packets are synchronized to the lowest ability. Okay, so each fragment itself is self-containing IP datagram transmitted over the various physical network. Physical network, it is fiber optics, Ethernet Cat7, Cat6, and PPP in point-to-point, just the wire connection. So each datagram re-encapsulated for each physical layer. So that is necessary because I have to talk to someone who is a poorer network environment than me, right? So header, this is the physical header information, a typical header information. So this is my 14 size messages. At some time, at that point, I have to divide to the smaller size. Then I only deliver to, this is FDDI, this is PPP. So I have to make it smaller. I have to do fragmented, meaning I have to say I am the start and there's a following. Okay, meaning I am the start, there is no following. I am the start, there's a following. Hey, I am in the middle, 64 shifted, and there's following. Hey, I'm in the middle, there I'm shifted 128, there's no following, meaning I am the last one. Okay, I'm the first one, I am the last one. It is saying in the header, and there's a packet length. There's my payload. Okay, this is how it works. In the fragmentation and reassembly. On the receiver, just consecutively receive these three. Receiver consecutively receive this 1, 2, 3, then start to decoding. Okay, I am the start. Okay, I start to open it. Oh, there's following. Okay, I didn't close it. Then, okay, shifted 64. Okay, oh, there's following. Okay, I didn't close it. Okay, shifted 128. Oh, you are the last. Okay, after 376, 512, 512. Okay, this is one packet. Then I can deliver to my upper layer. Clear? So just before the IP version 4, any question about it? No?
Professor, why do we need shift?
Hmm?
Why do we need offset between packets?
Okay, so without offset, I don't know how long is my packet. So in the packet, there is also the length of the packet. So length of packet meaning I offset 0, I'm the start, right? So 64 represent 512 data byte. Okay, without this, let's imagine there is no offset, meaning if the offset is 0, I'll start a new packet. Okay, this size meaning 64 bits here. Okay, without this, I don't know where to start it. So from here to there, here to there, here to there. If there is in the middle, this packet is wrong, then I don't need, without offset, I have to edit, right? But if something is missing at the tail, then all packet in the sequence, let's say there's 10 consecutive packets, then all the following will be contaminated. But if I have offset, shift, then this packet is somehow contaminated, then I can just replace this one. Then the following packets are just continuous concatenation, right? If there's no offset, just shift it, and everything will be concatenated right after that. Then if the one shift was 1 bit or a couple of bits are wrong, then whole 10 actual packets are lost.
Also, are you saying that it's like a marking point between
it is marking point, it is landmark. So this one from the whole packet, I am from here to here, here to here, here to here. I'm declaring my size.
Like, what determines the size of offset?
What determines the size of offset is the payload size.
Okay.
So this one payload is 512, which is 64. Then I'm so 64, 50, 112. Why? 64 by 8, 512. Bit to byte.
I see.
Okay. All right. Thank you, David. So we're going to talk about IP version 4. So we're also going to talk about IP version 6, but we're going to more focus on IP version 4. So IP version 4 is unique 32-bit number. Okay. When the IP version 4 is set, so people, who designer of this one, the architect of this one, architects of the IP thought, 64-bit is long enough to connect everybody. That was wrong, but at that time they didn't know the IP this successful this much. Everybody now, we're living in an 8 billion world. Almost everybody has their own IP, their own devices. I have like 10 devices, like you too, right? At least 2-3 devices, which require IP. Long time back, we didn't expect this much. They didn't expect this explosion. So IP version 4, long time ago, they thought it's long enough, large enough. So that identifies the interface and host or router and represent a dotted quad notation, meaning your IP is 192.68.0.250, something like this. We are using dotted. Every dot and every single number is 0 to 255, meaning 8 bits. 0 to 255, 0 to 255, 0 to 255. Okay, so this is 12. Why? 1, 2, 4, 8. 12. 1, 2, 4, 8, 16, 32. 34, right? We can repeat it, those that we are using this one. So, meaning 12 dot 13 dot, that's 1. So if I'm institute, I'm gonna need let's say I need SUNY Korea computer science. I may need 250 computer devices. Then I'm gonna ask this one as a network, and this one is depend on me. Then the router who care about those gives any packets coming from until this. Oh, that's for the CS for SUNY CS. Then under there, they don't really care. So it is managed by me. So I register to the authority and managed by me. So we call network level and host level. We're gonna talk about more deeply on this, okay? So let's think about the flat architecture. We're living in a hierarchical architecture. It has a high advantage. So let's think about the flat architecture. What's the wrong with this? Say I have Yonsei and SUNY K need to be connected. Meaning, let's say every host, every server has their own IP. Okay, in the middle, so router SUNY, router on Yonsei, maintain who is who. Okay, then how about in the middle, like KT? Okay, they are delivering their router information, everything to KT, everything KT. Because they don't have any hierarchical. These KTs are overloaded because they are not only 2, but there's multiple schools, multiple institutes. So KT router in the middle has to maintain all this information, meaning that it is impossible to do that, right? Say I want to connect it from me to in the Yonsei, then I go to my router, then router said, oh, it's not in my network, then go to the higher network, then router, okay, how can I connect to the 1, 2, 3, 4? Oh, they all think they're looking for all the routing tables. Okay, you need to go to that router. That computation take a while because I have to handle 3 million list. Then you have to go to that point. You have to go to that point. It is inefficient. We don't do this. Okay, we don't do the n square. We don't do n factorial algorithm like we do. We don't do that. Okay, we are doing n most n log n. Sometimes a log n. If it is n, that is weird thing. But if we have to search so many things, we don't do that. Okay, so we have to have the efficient. So something like this router in the middle has to maintain. If it is destination 1, 2, 3, 4, oh, go to left. At the destination 1, 2, 3, 5, oh, go to right. Forwarding tables are too long. There's too many works for the in the middle. Okay, so we change to hierarchical system and let's talk about why hierarchical is important. So IP addressing. So routing protocol need address to find the destination. So IP address is hierarchical to network part and host part. Okay, that is important. Let's think about the post system, post delivery system. So what do? I go to the, I'm in Korea, I'm in Incheon, I'm in Songdo, SUNY K, C413. Okay, this hierarchical, what does this gives me advantage? If I'm delivering from New York, Long Island, Stony Brook University, NCS building 320. Okay, if I'm delivering message to write this, what do I do? Okay, it is not there. So New York go to the USA. USA doesn't care about all the detail, but deliver to the Korea. Then in Korea doesn't care about the detail, but go to it's Incheon, handled to Incheon. Then Incheon there is handled to Songdo. The Songdo there, SUNY K in hierarchical. If you are the deliverer, you don't need to care about full address. You care about your corresponding addresses. Okay, if it is a packet delivery, millions of packets are delivered in between hosts. Then I have to have hierarchical. Okay, one is network part, one is network part in the messaging deliver, and one is host part. Host part in the detail. Okay, so class-based addressing. So IP version 4. So IP version 4 chooses class-based addressing. Class A, Class B, Class C, and Class D. Class E is not frequently used, but we only care about Class A, B, C, D. Class A means this portion is assigned to network. Class B, this portion is assigned to network. Class C, this portion. Class D, about this one in multicast in Class E. So let's focus on A, B, C first. Okay, A, concept of this. So I can give you, if my host is 256, 0 to 255, then this size, if this address is enough, then I can register. Like this, 255 is about a SUNY K. I can register. This one is 256 multiplied by 256 because I have 2 times of it. So let me calculate this. 256 multiplied 256, 65. Okay. This address, maybe this is adequate for Yonsei University. How about this? 256 by 256 by 256. This is 16 million. Maybe this is a million. Maybe this is proper for Seoul. Okay, something like this. Why? So Seoul can handle this much IP. Yonsei can handle this much IP. SUNY K, this can be handled. So network is assigned. Network is maintained. So wherever the packet is coming to my network side, so they don't really handle, but they just forward it in the Seoul. They just forward to Yonsei. They just forward to SUNY Korea. So they divide IP address. Okay, what is network and what is host? Host is C413, the detail. The network says, oh, SUNY Korea, Yonsei University, then higher hierarchy. Okay, so we'll talk about this. So Class A. Class A is this much, 16 million hosts per network. So who need this big IP address? Like MIT, maybe need it. Maybe Korea may need it. Maybe SNU, Seoul University, Seoul National University may need it. Okay, Harvard may need it. This kind of school, this kind of level. And Class B may maintain 65,000. Maybe IGC, maybe Yonsei University, maybe Songdo, something like that level. Class C, 254, host maybe the CS department of the SUNY Korea. That kind of information, that kind of level. Then this Class A, B, C, Class A is very hard to obtain. Why? Because it's so limited. Long time ago, who needed first? They already take up. So IP version is already overbooked. And if you need your own static IP, it is almost impossible to get it from the authority. But you may ask your institute to share with them that kind of path is possible. But maintaining from the scratch, I want to have Class A network. That is not possible in 2020. Maybe 1990 it was possible, but not now. So how do you solve this? We have solution to that, and we call the NAT. And maybe DHCP. We're going to talk about this today too. So I want you to understand the size of network needed. Why is it important? Class A. So this much is assigned to network. This much is assigned to host. Meaning the network is registered. Under the network, the institute maintains. Okay, bigger the better. But it is also the rare and it's very expensive to obtain. Okay, in Korea, I think one or two. SNU has it, and KT has a Class A. KT and SNU, I think only two institutes has a Class A. And Class C like this, and it is usually given by the ISPs, Internet Service Providers. Okay, if I want to have my own network, I can request. But these days, everything does not work in this way. Everything works on the cloud. And they are maintained somehow. We are not asking and we are not admitting those. Okay. So think of postal addresses. Okay, so mail addresses, zip code, and street, building, and room, and name of recipient, all hierarchical. Okay. So delivering mail, deliver letter to the post office according to the zip code, and assign letter to the mailman covering that street, and drop the letter into the mailbox for the building or room. Give letter to the appropriate person. Okay, they're all hierarchical. So IP is just copying the postal system, and they are doing exactly the same, the hierarchical method. So hierarchical in IP addresses. So divide into network and host part. Oh, we talked about this, right? Divide the network and host bits. So 12, 13, 158.0. Okay, something like 24 means my subnet mask is to 24. So from here to here is 32. 8, 8, 8, 8, meaning 24. Until here is network. From here is the host. Okay, this /24 means this one information. So subnetting. So subnetting is critical for not clearly specified class A, B, C. So how do you subnetting? So we will talk about this. So class B address, for example, class B is 16, and 16 is divided to network, the host. If I do subnetting to 24, this means 24. I means I'm gonna use this one as a network, my host. Even I have the wider one, meaning, so network number, host ID. In the middle, the subnet ID. What is the advantage of it? So let's say I am MIT. Let's say I am IGC. I have class B information. So I have class B, but if I give it to the host address, what should I do? I just give randomly to everybody who asked? No, that's not hierarchical method. So I want to maintain my hierarchical. So IGC open, I have class B information, class B network. So everybody who need it, give me a request, send me a ticket. Then, we are CS department, we need it. We are mechanical, and there is a George Mason, and there is a C. Let's say there is EE. We don't have EE. Something like that. Oh, you know what? If CS and mechanical, you have to do like this. They do. Then SUNY, hierarchy CS, SUNY hierarchical ME. Then they have 5 schools, FIT, and something. Then how can you represent these in the middle? Even I have class B. That's a subnetting. So I make subnet ID. So this is authority maintained. Okay. So I can give you this subnet ID classifies who is SUNY K CS. Then who is a SUNY K MEC? Who is FIT? Designer, something like this. Who was a GMU, and EE, something like this. So here is a subnet ID. From there, I can collect my IP address. From here, I can collect my IP addresses. So subnet ID works in this way to maintain the hierarchical more flexible and strictly following the hierarchical mechanism. So an example of the subnetting. So subnetting, so let's say my address and subnetting, this is 25, this is 25, this is 24. So this one, 34, 34. So this router and my router here, my router in here, My router. Yeah. So my router comes in 128.96.34.1. So 128.96.34 at 15. So 1 is 128 meanings. So let me talk about what is 1. 128.96.34.1. If you look at this, 1 is 0, 0, 0, 0, 0, 0, 0, 1. This one, 128.96.34.15. 15 meaning 0, 0, 0, 0, 1, 2, 4, 8, 16. Okay. Oop. So if I set the 25, the first bit on the last one should be fixed, same as before. Okay, move on to this one. This is 25. Let's look at this one. This guy is 24. 128.96.33.1. This guy is 128.33.14. Meaning this network can maintain up to 0 to 255. 256 guy. How about this guy? Because it is limited by 1 bit, therefore I can maintain 0 to 120, 256, 123, 256, 256 divided by 128, right? Oh, wait, 256 divided by 2, 120. Yep. So 0 to 127, because it's 128. So this network can handle up to 128 computers. This network can handle up to 256 network. This network can handle 128 devices. Okay, based on your subnet network. So if the CS, if you're comparing to the CS to DTS, DTS does not require that much computer, but CS require much more computers. Meaning I can request bigger network. DTS may satisfy with 128 bits. Okay, that's the example of the subnetting. So easier it is because I have fully hierarchical mechanism. Then it is easier to route packets. Say 24 meaning. So this one is 24. So until this point is my network. Meaning, where is my 5.6.25? Then I don't really care about 25. I only care about if you're talking to these groups, then go to my right. Okay, how about 1, 2, 3, 1.2.3.250. So I don't really care about these hosts, but if you're looking for these guys, then you can go to left. This router can say. Okay, the routing tables are much simpler than before. I don't need to maintain all the hosts in there, but I only need to group them. Then routing tables are much simpler. They're more intuitive and simple to maintain. So the routing table is simplified to this one. I don't care if you're comparing the previous one. So routing table, all have to care about which host is where, which host is where. From here, because I have subnetting mechanism. So who's my network? Who's my host? I know where it is. Then I can just forward it left and right more easily. Okay. So it is also easy to add new host. So if it is new host added previously, I have to register to my router, then go to that higher router, also maintain my update. But in here, if I'm just adding with a 213, I only need to update my router. My higher router doesn't need to, because whoever ends in here will be forwarded to me. That's my job. Okay, this is SUNY Korea's job, not the KT's job. Okay, so whenever you plug into the wall, SUNY Korea can notice and communicate sometimes, then connect it. I don't need to be connected and notice to SUNY Korea to the KT, and KT to the world back. I don't need to do that. So I just need to my own authority, then maintain my network. Okay. So this class-based is too strict. It is good for communication, but what if we are using the class list? Let's talk about the class list domain routing. We call the CRDR. So rather than strictly following until here is my network. Hey, how about this? How about there? Hey, about there, I can divide wherever I want to. Then we call the class list. Class ABC. No, don't talk about ABC, but let's talk about class list. I can flexibly maintain. I can flexibly play. So IP mask is more flexible. I don't need to be the puncture at that point. No, I don't need the whole wideband, but no, I don't need the whole length of it. I just need one more, which means double my capacity. I think that is enough for me. Okay, that kind of mechanism, and we call this class list because it violates class-based. Okay, so class list is hierarchical address allocation, and prefix, the network part, is key to internet scalability. Then it is more flexible based on my request, based on I need. Then it is more flexible because the higher hierarchy doesn't care, but the lower hierarchy handles the detail. Okay, then from there, okay, then it's more hierarchy, and we are using this in today's technology. And routing protocol and packets and forwarding based on the prefixes. And today, so routing tables contains about 200,000 prefixes. Okay, that is doable. If you talk a million, if you talk about the billion, we cannot handle. But if you can handle the 200,000, if it's all I have to do, I think I can handle. Okay, all the routing necessary. So obtaining a block of addresses. So how can I obtain a class A network? So separation of the control, we separate the prefix and addresses. Prefix is assigned to institute. Now we understand what is institute assigned to network. And assigned by the institute, their node, my computers. So who assigned the prefixes? So internet corporations or ISP, internet service provider, for assign names and numbers and allocate the large address blocks to regional internet register. So KOR has a bunch of it, and JPN and CH China has their own the IP chunks. So RIR's regional internet registry. ARIN is America Registry for Internet Numbers. So we have Asia in Korea. So allocate addresses block within their regions and allocate to internet service provider and large institute. So SUNY Korea only using the KT or SKT, but if your institute is large enough, you don't need to rely on a KT, but using the SNU network. But SNU network kind of things does not work properly, because KTs are periodically updating for their services. So they are updating physical routers every 2 years. The SUNY, SNU cannot handle that fast. Okay, so ISP, so we have KT, SKT, and LGT. We used to have many, but they are all merged to the bigger company, So ISP in Korea is about 3. In US, there's Verizon and the AT&T and Sprint, and about 4 major companies. Then divide the whole nation. So allocate address blocks to their customers. So who may in turn allocate their to customers. Okay. So who think the 32 bits are enough? That's about 8 billion, 4 billion, right? Million and billion, about 4 billion. So we are living about 8 billion population, and 50% of the world using internet. Look like 4 billion is large enough, isn't it? Don't you think so? But if you think about yourself, I'm using about 10 computers. With my smartphone, my smartwatch, my iPad, my notebook, my computers, and I believe you are very similar to me. 5 to 10. How about your family? About 10 times. Okay. How about my car has their own IP, needed their own IP because they need to be connected. My kickboard, my air conditioner needed. In the world of IoT, everybody needs a one device, right? So that is not enough. Then how can you solve this? So computers are your smartphone, your routers and tanks, and all the military devices, your toasters for the IoT world may need IP addresses. So, okay, so we understand why is it necessary, right? So we understand why 32-bit IP address is not long enough. Then how can you solve this? Okay, let's think about for 3 minutes and let's discuss. I think I was the only one to talk. So let's think about the issues. Why is it necessary? And let's talk about this. And I'm gonna pick 310. This. I'm gonna ask Yeun and Hojin and Seungjae. So question is, so 32-bit IP is not long enough. Then how can you solve this? So your own idea. Okay. Let's think about for 2 minutes and let's discuss. Okay, while you guys are thinking, I'm going to share who apologize.
You have some.
Okay.
A group of people here at Google that have.
Can you hear the voice from the video? No?
Yes.
You can hear?
Yes.
Okay.
We can hear.
Here, but you have some.
So he's a Binsurf who designed the IP version 4.
A group of people here at Google that have almost single-handedly pushed us to implement IPv6. The reason that's so important is that the IPv4 address space only has 32 bits. It's 4.3 billion terminations. I made the decision in 1977 that the address space could be 32 bits and it would be enough. I thought we were doing an experiment. I thought, that we didn't know if this thing was going to work, and surely 4.3 billion terminations is enough for an experiment. I mean, even the Defense Department probably couldn't use that many termination points. So I thought what would happen is if we demonstrated this capability, then we would in fact do a production engineering job with it. Well, the experiment never ended. Here it is, 2010. We're running out of address space. We need larger address space. We actually argued 32 bits, 128 bits, and variable length. The variable length guys lost because the programmers said it's going to chew up a bunch of computer cycles to find the fields in the packets. So they didn't want to do that. So that was out the door. And finally, because nobody can make up their minds, and I'm sitting there in the Defense Department trying to get this program to move ahead. We haven't built anything. I said, it's 32 bits, that's it, let's go do something. So here we are, my fault. On the other hand, if I had stood up and said, we need 128 bits of address space because this is going to be the world's backbone in, 25 or 30 years, they'd look at me and say, boy, are you out of it. Internationalized domain names. Remember I showed you all the distribution.
Okay. So he's the one who made the IP version 4. Like he said, that he thought it is experiment, and it's still it is backbone of the world now. Okay. Now he's at Google. Okay, back to the point of my IP. So it happens, right? It happens 32-bit. So how can you solve this? Okay. Yeon, what's the solution? No, Yeon not here.
I'm here, but I'm not sure. Sorry.
Okay. And Hojin?
Yes.
Yeah. So I love to hear the crazy idea, please.
Crazy, nothing crazy, but well, 32-bit. Well, there's a lot of devices that, and well, most countries now have internets, and 32-bit would not be enough to accommodate for all of those devices, I think. So maybe just use a larger bit, like 128.
Use a longer bit, you mean? Okay, that's a solution. Okay. Sungjae?
Not sure about it. I'm sorry.
Okay. Yeonshik? Yeonshik is here. So Yeonshik, for the, if you want to talk to me, please stay after the class, then we can discuss about the score. Okay. Yeonshik, are you listening? Okay, I hope so. All right, so people thought, man, we need a solution, and how can you solve this? Any idea from everybody? How can you solve this?
IPv6.
IPv6, okay. Anyone else? So to do IPv6, we have to change so many things, isn't it? So IPv6 is basically longer bits. So 32 to 128. But to change it, we have to change so many things in the middle. So all routers over the world, they set it to the 32 bits. Okay. So already there is already bunch of the networks, bunch of devices already installed. Right. I don't think IPv6 is the solution. How can I solve this? Any idea? No? Okay, so IPv6, of course, if we implement it, the long term, 2 to the power 128, which is long enough, is 4 billion multiply 4 billion multiply 4 billion multiply 4 billion devices, which is large enough, right? And or the short-term solution, limping along with the IP version 4. Okay, something like private addresses. Okay, something like a NAT, network address translation, or something like DHCP. Okay, let's talk about the private addresses. Private addresses are not successful idea. Private address, I can have periodically my address. There is the main guy who maintains, I can update my IP addresses by round table if I need it. And there is a one guy who maintains, okay, if you're coming to here, go to there, parameter address, jumping all over the places. That means, so the backbone router changed to IP version 6. And there is IP version 4 devices, limping. We also call the tunneling. So how they connect to the IP version 4 to IP version 6? How they connected? So it's smarter to dumber, dumber to smarter. So if the dumber just talk to smarter guy, it's not an issue because smart guy understand that. And smart guy want to talk to dumber. Then they have to translate the dumber language, then they can understand it. Okay, the translating in between smart guy and dumber guy. And DHCP meaning, so I only have one IP out of 4 billion. One IP, 4 billion. Okay, from there I maintain that roughly. So I only have one IP, but I can maintain about 1 million devices. Okay, and where it goes outside, then every hostess name is coming name after this one, the leader. Then leader's name gone there, and when it comes back, okay, leader's C, okay, leader. Then there's an optional field. From here, okay, you go to this host, you go to this host. That's the DHCP. This is the industrial winner, and we are all using this. 192, 168, 1 dot something is DHCP, basic DHCP. So above there, there's one IP address for the institute. So SUNY Korea has about 10 to 30 IP addresses, and they maintain thousands of devices. How they using it? We don't use IPv6. IPv6 is a conception. We thought 10 years ago, we thought IPv6, oh, there's a solution. But you know what? In the end, IPv6 also depleted, because if you think about the IoT, billions of devices are produced every day, every year, billions of IoT devices produced. Then what you're gonna do? Maybe in 10 to 20 years, that your billion concept is not working. Even you have those things. They may have subordinate, right? So Samsung itself produces billion devices a year. They all need their own IP. No, it doesn't work. So the DHCP, if I give you one institute, if I give you one IP, then you maintain the under there. SUNY Korea has one leader or a couple of leader IP addresses. So they maintain their subordinate. Wherever they want to go to outside, they are going as a name of this IP. Then when it comes back, okay, you know what, there is an optional field, then I can exactly deliver to you. Okay, that's the industry winner, DHCP. We are using this. Okay, so hard policy question. So how much address space per geographic region? How can we divide? So what is right way to do? So class A, who's giving to who? By the continent? By the country? So if I am since I am in Korea, I may ask, okay, whoever who uses more internet should have more IP. But if I'm in Africa, oh, I have many population, I have more potential to use it. So I should have it, right? If I'm China, oh, you should give me everything to me because I have a potential, I have a users. So what is the fairness to everybody? So equal amount for country, so proportional to the population. So addresses already allocated. What happened is we need to reshuffle it to properly. So now most of the IP address, the good IP address given to the US. Because they started, okay, I understand that. Since we changed, so we should distribute it properly. The US will listen to us? No. So address space portability. So keep your address block. Keep your address block when you change a provider. So we call this handover issues. So we're going to talk about this. So keep your address block when you change the providers. Meaning, I want to have my addresses, even I change from KT to SKT. Okay. Oh, that is cool, right? I don't depend on my ISP. I can maintain my own ID. So pro is avoid having to renumber your equipment. The cons are reduce the effectiveness of the address aggregation, meaning your ISP will never allow you to do that. Okay. So keep the address registry up to date. So let's say higher. There is the authority, right? So we call the registry. So how they maintain? So updating up there, updating up there, updating up there. So registry on top of that. They have so many things to do, right? So like every day they're plug into new router, plug into new router, plug into new router. So how can they merge and new acquisition? So delegation of the address block to the customer. And as a result, registers are out of our update. It is not able to maintain properly. The higher rank, the higher authority, they don't have ability. And the lower ability, so we call distributed network. So they have to their own. Then over there, they have take responsible by the leader, responsible by leader, leader to leaders, and above that, they're just watching it, observing it. They don't do nothing. So that's the, therefore we don't have the observer. So we have the freedom of the internet. Okay. All right. Okay, this is what we have today. Any question? So IPv5 was, I think it was discussed between IPv4 and IPv5, and IPv4 is selected. So it is a 5-digit, I believe, if you read through carefully. This is first implemented in 1973 and 1979, and I think 4 addresses or 5 addresses. 3 dots, the 4 or 5. Then 4 of them, 4 is selected. Okay.
Then wouldn't the 4 dots be way better for now, because that would be more than sufficient for the population of the world?
Okay. Yeah. Then 5 dot. What if in the 10 to 20 years?
All right.
How can estimate? So we are exploded much faster than expected, right? Then we redesigning, that's not clever. We have to survive in a given environment. That is why the DHCP wins, and that is the industry's choice. DHCP. Yeah.
Professor?
Yep.
Then why don't we just make it big from the first, like IPv8 or IPv10?
Okay, then longer, right? Your header is more complex. So in the middle, we implemented, so all the word is already implemented in version 4. Can we update the version 8? Okay, so until the 2020, December 31st, 00. From there to the 1 second later, everybody updated to version 8. Is it possible? It's not possible, because you are not dealing with the only devices who is equipped, but we also have the nuclear machine. We also have submarine. We also have the missile system, right? They're on their IP. So updating everything in one time is not possible. So if that was possible, we had to make a right decision a long time ago. We have to estimate our future more properly, but we did it. Like he apologized. So they thought it is experimental setup. Okay, version 4 is 4 billion. Oh, okay. So the same as the Earth's population, that should be enough, right? Then you know what? So people start to use 10 to 20 devices. An institute using 10 to 20 devices per people. We have to have more. How about IP 5 dot? You know what? In 10 to 20 years, 5 dots is like, oh, extended more. That concept, I don't think it is not right, and it is not able to update everybody after this and do that. No, that's not possible, because we already implemented so many routers and so many devices already. We cannot update. Okay, we cannot estimate the consequences. That is why we cannot do that. Okay.
Thank you.
Okay. Okay. Any more questions? No. So if you want to talk to me personally, you may stay in the in this Zoom, then we can talk about your questions or private concern. All right. So I will upload the makeup exam, and it will be a take-home exam, and I will upload the final project, and I will release the homework too today. Okay, I promise you. I'm too lazy. I'm sorry, and I will promise you to deliver today.